Yeah. I would like to thank the people who invited me. They are also friends for since a few years. I will be talking about quantum confinement and in nanoscale superconductors. And these are my collaborators, Sang, Kovaci, Theorem, Milosevic was here, and also Arkady Shanenko. So some of the things I will be showing have already been touched by other people. And so, for example, if you have quantum confinement, the system changes in different ways. First of all, you discretize the energy, and the discretization becomes larger the smaller the dimension of the system, and as a consequence, the density of states changes. And that will have an influence on superconductivity. A second thing is that your distribution of your electrons or of your Cooper pairs is no longer being homogeneous over the system. And this is an example for the quantum wire, the center of the quantum wire, and how the superconducting condensate changes with the radius, and you see it's 0 here. So quantum confinement discretized energy levels, leads to a non-uniform electron distribution, and it changes the density of states. This is also the idea which Antonio Bianconi tries to put forward, in which he says, look, you use quantum confined states, and that leads to quantum engineered multi-band superconductors. And the way to see that is as follows. If you confine your system, for example, to a slab, then your three-dimensional energy spectrum is discretized in subbands. And the electrons who participate in the formation of Cooper pairs are around the Fermi level in a window which is given by the Debye frequency. Now, if I change the thickness or the strength of the confinement, you see that more subbands or electrons belonging to more subbands can participate. Okay? Not only these electrons in the first subband, but also these electrons in the second subband. And so if I look at the number of states within this Debye window, that's going to change if I change the confinement strength. This is an example for a wire. This is an example for the film. In the film, you have a nice periodic behavior, and the reason is that each time when the thickness changes with half the Fermi level, then you get an extra subband penetrating this Debye window. Now let's make a simple estimate. This result was shown already before. So if TC or the band gap is given by this BCS expression, let's take aluminum. Suppose that the density of states changes with a factor of 2. This would change the TC with a factor of 60. Of course, this is very simple reasoning, but at least it gives you or motivates you to look a little bit more careful into this problem. Okay? And this was in fact proposed many years ago by Blood and Thompson, who made a very simple multi-band BCS theory and found those shape resonances. Now the theory to describe these systems in a mesoscopic regime, that's the regime where the thickness of your system is of the order of the Ginzburg-Landau coherence length. There you use simply the Ginzburg-Landau theory, and where you have a spatial dependent order parameter, and you simply demand that the current flowing out of your superconductor is 0. In fact, it means that the derivative of your order parameter is 0. So that means that at boundary, the order parameter is different from 0. In the nanoscopic regime, then you are talking about dimensions of the order of a few Fermi wavelength. Then quantum confinement is important, and the single particle wave functions are 0 at the boundary. That makes a big difference here. And there you can still discriminate or put the system in two different classes: nanofilms, nanowires, and grains, which were discussed by the previous speaker. In nanofilms, you have appreciable size resonance effects, and because of the non-homogeneous distribution of your weight, of your order parameter, you can have new Andreev states, okay, which now are no longer induced by your magnetic field. Right? Think about the vortex, but now they are induced by quantum effects. They mean that quantum effects leads to a non-homogeneous orthoparameter. In grains, you also have this finite n effect. And so the theory which we will be using is the Bogoliubov-Degenn theory. So I'm in this part. So first of all, the density of states effect. That leads to a critical temperature which depends on the size of your system. For example, there have been experiments on aluminum nanowires, and if they decrease the diameter of the wires, then they found that the TC could increase with at least 50%. Okay? The red symbols is the experiment, and this gray area is the theory. We find a lot of fluctuations. That's because if you move or you change the thickness of your wire, then different levels move through your Fermi level, and experimentally, probably the wires are not completely uniform, etc. Okay? But you see, you find pretty good agreement. Similar experiments have been done on tin by using simply electroposition into porous membranes. In nanofilms, people have measured similar effects. So this is also aluminum, and also see the thickness of the film if it decreases. This was a tunneling experiment done at Sydney, the group of Bob Clark, where they found that the gap increases if you make the film thin. Okay? So the message here is, at least if you take aluminum and tin, that if you make the system smaller and smaller, the TC increases. So what about quantum size effects? Namely, the fact that your TC should oscillate when you change the thickness. And so there have been a set of experiments where they put lead on silicon 111 substrate. The nice thing is there that this lead will grow epitaxially on this substrate, and that you can really control the growth almost monolayer by monolayer. And a few years ago, we collected all the experimental results which were available at that moment. These are experimental results of different groups, also using different techniques. Some of them are resistance measurements, others are tunneling measurements, they are also magnetization measurements. And you see that they vary a lot. If you have a positive mind, then you can say, look, there are indeed some oscillations in the TC versus the thickness, okay? But they are not as strong as what the theory would predict. So here we made a comparison of these blue dots here with our theory, but where we had to fiddle a little bit, we had to change the coupling strength there. And our reason was, well, that probably the phonons also have, or are also influenced by the thickness. Okay? I think more clear quantum size effects were found in superconducting nanoparticles, and these are the experiments by Sarita Bose, who will be the last speaker here, and where they did an STM measurement and measured, in fact, the superconducting gap versus the particle height. In fact, they had not spheres, but they had more or less cut spheres. And you see clearly from indium oscillations, and that has to do how many energy levels are within this Tabaia window. In lead, you see the opposite behavior, it goes down. I will not discuss why lead is different. It's a higher coupling superconductors, but we have a few ideas why this goes down. The main topic of my talk is how will the non-uniform electron or superconducting condensate influence the vortex states. Yeah? So if you take mesoscopic structures and you take, for example, a square, and this is the phase diagram of this superconductor. So here, this is the magnetic field, and this is nothing like 1 minus T. So here it's Tc, and here I decrease temperature. Okay, so this is the superconducting area for a superconducting square, Meissner state, one vortex in your square, 2 vortices, 3, 4, 5, etc. You can also have an area here where the 2 vortices merge into a single vortex, which is like which we call a multi or a giant vortex. Okay? So these configurations are determined by the fact that the vortices repel each other, and also by the fact that the vortices are repelled by the boundary. Okay? And it's this competition which determines what type of vortex configuration you have. For example, here, the boundary effect is going to dominate and simply make the 2 vortices to coalesce. So you have giant vortices here, the vorticity larger than 1. You have non-triangle configurations here, a square, for example. And you also have some really interesting configurations where, although the vorticity is 3, you have 4 vortices, and in the center you have an anti-vortex. Okay? So this configuration nucleates because the arrangement of vortices has the same symmetry as your boundary. Okay? So these vortex configurations have been observed experimentally using bitter decoration techniques, also by using multiple tunnel junction methods. It was shown that it's possible to observe giant vortices, also ballistic Hall micromagnetometer, and STM. Those vortex, anti-vortex configurations at this moment have not been observed yet. Now, in nanofilms, we have an additional ingredient. If you look simply at your order parameter versus the thickness of the film, and that's for different films, you have the fact that your superconducting condensates oscillates. And that's nothing else what's called the Gibbs phenomenon. Yeah? You see the same thing in squares. Okay? So this is simply a square, and I simply shown the dimensions of the square and keeps the Fermi energy the same. And you see that the oscillations in your superconducting condensate can change a lot depending on the size of your sample, or if you change the Fermi wavelength. So that means that now we have an additional ingredient, namely that the vortices will be attracted to regions with low superconductivity. Okay? But because there it will have to destroy less superconductivity in order to nucleate. So our approach is the Bogoliubov-Degenn equation. This has been discussed already before. So it's simply 2 coupled differential equations. If you forget this term, it's simply the Schrödinger equation of a free particle. If you add a magnetic field, you have to replace this kinetic term by this here. And then you have coupling, and the coupling is through this pairing interaction between them. N is a quantum number. It characterizes your state in particular subband. Okay? So it contains a subband index and also your wave vector. Okay?
For the N, you are using an attractive Hadamard model or a lattice?
Simply, no, this is a continuous model. Okay?
Ah,
so it's simply a delta a contact interaction. Okay? Yes. That's this G, like a phone cup. Okay? So you get a large set of coupled differential equations, and that you calculate self-consistently the superconducting order parameter, and by plugging these in there, and then the chemical potential is fixed by the electron density. Okay? So that's the traditional Bogoliubov-Degenn equation approach. So what's the effect of quantum confinement on vortex matter? If you would look simply at conventional superconductors, then the Fermi wave vector multiplied with the coherence length is usually a large number, typically 1,000 or even more. If you want to see quantum confinement effects, then the size of your sample has to be of the order of the Fermi wavelength, and that's much smaller than the coherence length. And the coherence length, that's more or less the size of your vortex. So that simply tells you that it's impossible to nucleate vortices in such a sample. Okay? So you will have to go to systems where this product is small. Let's say high DC superconductors. But then because coherence length is small, you have to go to very tiny systems, so which is also not really realistic. But there's another system. For example, if you take graphene and put it on a superconductor, then you can induce superconductivity in your graphene using the proximity effect. For example, if you take graphene on lead, and let's say you take a flake of 400 nanometers by 400 nanometers, that can nucleate many vortices, this Kf multiplied by psi 0 factor can be varied between 0.1 and 10 by simply changing the density of electrons in your graphene by using the field effect. Okay? So if you change the formula from 10 to 100 milli-electron volt, and that's something which people do almost continuously. Also this work, which I will be discussing, will also have some analogies with optical trapped gases. Okay, so when we do our calculation, we solve this differential equation, and we have to perform numerical iterations because of the self-consistency. And I will give you a flavor of how this works. So let's take a sample of 5 times the coherence length, and we put certain magnetic field in it such that there are 2 vortices nucleated. Okay? And if you solve the Ginzburg-Landau theory, you would have the 2 vortices sitting along here, along the diagonal. So now I simply look at the tolerance, which is simply the difference, or the largest difference between the order parameter in your square, and I look how this varies as function of the iteration step. Okay? And the dashed line is nothing else than the free energy. So I put my computer in this configuration, and I let computer run. So what you see is the tolerance decreases and then suddenly increases. If I look at the vortex configuration, it has changed from those 2 vortices to 4 vortices and 1 giant vortex in the center. Okay? That happens continuously. And then if I keep or let my computer run, keeps running, then what happens is that 2 of those vortices annihilate with this anti-vortex, and I get this configuration, which is very different from what you get from Ginzburg-Landau here. Good. So we do this calculation for different magnetic fields. This is the free energy. So this is the free energy for the Meissner state, 1 vortex in my square, 2 vortices, 3, 4. Okay? Now, as I told you, in the Ginzburg-Landau theory, you only have those repulsive interactions which determine the vortex configuration. But here you have an additional component that's an attractive interaction between the vortex and the place where you have the minimal band gap or the minimal value of the autoparameter. And for example, if I take the L equal to 1 configuration, Ginzburg-Landau theory will tell you that the vortex sits in the center. No, in this case, the vortex sits off-center, so it's really asymmetric. Okay? And this is simply the phase, and you see that indeed, that's where the vortex is. The phase changes with 2 pi. So how can we understand that? This is simply the order parameter at 0 temperature, at 0 magnetic field, and this curve here is along the diagonal. Okay? So you see in the center, you have enhanced value of the order parameter. So if I want to put the vortex in the center, it will cost me a lot of energy, and as a consequence, the vortex prefers to sit in one of those 4 places. So all those 4 places are equivalent, and that's why you get this very asymmetric configuration. For 2 vortices, they are sit like here. But what you see is that for even vorticity, you have the largest stability range, L equal to 2 and L equal to 4 also.
Because we have the diagonal maximum.
And normally, Ginzburg-Landau theory will tell they will sit like this. Now, the next thing what I will do is I will keep the size of my sample, but simply change the Fermi wavelength. Okay? Change the electron density. And you see, the picture is really quite different. And if I look now at the spatial distribution of the order parameter, I see that in the center it's quite flat here. Okay? I put one vortex in here, now it's sitting in the center. Okay? Two vortices, it sits here and here, or here and here. Okay? Three vortices, one sits here, 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 and I put an anti-vortex in the center. Okay? In this particular case, odd vorticity has the largest stability range. So by simply changing the density in your sample, the vortex structure changes completely. Okay? So to wrap up this part of my talk, the conventional vortex states, the one you find with Ginzburg-Lambda theory, are like these. So the 2 are on the diagonal, the 3 are like this, 4 like that, 5 like that. And if we include this quantum confinement effect, we find additional type of vortices. Asymmetric ones, we also have ones quite asymmetric, 3, 4, they are rotated, 5 like that. You get vortex states which are parallel to one of the sides of your sample. Also giant vortices, but that's also what you find in Ginzburg-Lambda theory. And you can also get vortex, anti-vortex molecules. So the oscillator pattern or the autoparameter is very sensitive to this Kf multiplied by psi 0, and that will cause different vortex configurations even in samples with the same dimensions. So in nanoscale superconductors, we found, as compared to the results in Ginzburg-Lambda theory, that this favors guide vortices, but favors anti-vortices. So this particular case here, where I have 4 vortices and 1 giant vortex in the center, that's more stable if you have quantum confinement than in Ginzburg-Lambda theory, where they have a very small range of stability. And another interesting thing is that the distance between this anti-vortex and the vortex is about the coherence length, while in the Ginzburg-Lambda theory it was usually smaller, and that's probably the reason why people up to now have not discovered this new type of vortex configuration. Okay. We also found if the vortex configuration matches the one which you find from Ginzburg-Lambda theory, then you have a larger stability range, and that's also what you would expect. Effect of temperature. How many minutes do I have?
7 questions.
7. Okay, so this is the case in which I have one vortex sitting in the center of my square, and you see at some particular temperature, 0 temperature, and that's what you normally find. So the order parameter goes to 0, and then you have those oscillations due to your quantum confinement, and if you increase temperature, those oscillations disappear gradually. So then you can also define a size of your vortex core, which is like the coherence length. So we follow the approach of Kramer and Pesch. And that's what we found. So this is the inverse of this size, or it's nothing else than this square, versus the temperature. Okay. Notice also that this does not go to 1, and the reason is, of course, that we have a magnetic field applied different from 0, so the superconducting condensate is destroyed before you reach DC. This is normally what you expect, a zero magnetic field, that this here has this 1 minus TTC dependence. More or less, this is what you find at higher temperature. You can define some temperature scale where this ratio of the temperatures equals to this. So that means simply that the Fermi wavelength is of the same order as the coherence length. Okay? So that simply means that here you are in the Ginzburg-Lambda regime, and here you are in the quantum regime. So if you look at the effect of temperature on my phase diagram, so now this is T versus phi. You see that we do not go up to DC. That is due to quantum size effects. At high temperature, so that means close to the superconductor normal boundary, you get the conventional vortex states, which typically have the C4 symmetry. So one vortex, a giant vortex, L equal to 3 here, that's this one here. So 4 vortices and 1 anti-vortex. And if you go deeper into the superconducting region, you find those unconventional vortex states, okay? Asymmetric, etc. Okay? So the last part of my talk is what's the effect of impurities. We know that impurities have been used in superconductivity in order to see or detect the symmetry of the superconducting state, for example, in D-wave superconductors. Also to identify topological superconductors. And they also, of course, typically use the pin vortices in order to enhance the critical current. Also, if you have a strong disorder, you can have the superconductor-insulator transition, and you can even localize Cooper pairs. We also know that there's this Anderson theorem, which tells you if the density of impurities, non-magnetic impurities, is not too large, then the bulk thermodynamic properties are not changed. Okay? And that the impurities have only a local effect on your superconductor and on the outer parameter and the dust. I will show you that in nanoscale superconductors, this theorem breaks down. And that the superconductors can influence strongly the superconducting properties, and that even depends on the position of the superconductor, of the impurity, and also on the width of your wire. So, as a model system, I take simply a wire here, and I put an impurity somewhere here in the wire. And then I use periodic boundary conditions, and I take my computational unit cell sufficiently large that the results will not depend on Lx. The impurity I simply model by a Gaussian, and I take the parameter such that U0, the strength of my impurity, is sufficiently large that it completely destroys superconductivity at the center of the impurity, and the size of the impurity is much smaller than the width of my wire. I can discriminate two different cases, the off-resonant case and the resonant case. The resonant case, then I have increase of TC. Off-resonance case, usually TC is lower than the bulk value. Okay? So this is the average, spatial average autoparameter as function of the wire width. And you see this is an oscillating function. So I look at this state and at this state. So at this state here, the autoparameter across the wire has this type of behavior. Okay? For a wire which is in the off-resonant case, non-resonant case, the autoparameter is like that here. It's much less. Okay? I need still one additional ingredient. The quasi-particle spectrum, I can create a hand waving. Okay? These are the different subbands here. Okay? This is a case with 3 subbands. To get a quasi-particle spectrum, I refer everything to the Fermi level. So I simply flip everything what's below upwards here. Okay? And then the pairing interaction induces here a gap. Okay? So in fact, I have 3 superconducting condensates with a different gap. Okay? So if there is no impurity present, in the resonant case, I have this spectrum. And if I look now to the local density of states, in this point, I see 2 gaps, in fact. Okay? I see a gap here and a gap here. And the smallest gap is due to this, sorry, it's too fast. It's due to this part here, and, sorry, yes, to this here, and the large gap is due to this here. This has a larger density of states because you see clearly that the density of states here is larger. In the case of the off-resonant case, I see only, in essence, 1 gap. Okay? If I put the impurity in this position here, I see only 1 gap, and the reason is that here, at this position, the J equal to 1 state has a maximum in the center, but the J equal to 2 state has a node there and will not contribute to the local density of states. Okay? So if you put an impurity, and I will have to flash the results, you see that putting the impurity here or in the center of it has an influence on the order parameter. And also it has an influence on how the order parameter is recovered along this wire. Okay, so we looked at what's the effect on the Josephson current. I will flash only the results. In the resonant case, if I put in the clean limit, it's this here, if I increase the current, I see that if I put the impurity at the center, it blocks the current more than if I put the impurity at the edge here. And that's because in the resonant case, the current is mostly carried in the center. In the off-resonant case, the situation is a little bit different. There the current is carried by two stripes along here. And you see that we have there the opposite behavior, that if I put the impurity here closer to the edge, it has a larger current than if I put it in the center, and also the currents are small. So I flash my conclusion. Quantum confinement leads to quantum engineered multiband superconductors, and in this talk I addressed the inhomogeneous spatial distribution of the superconductor condensate that leads to novel vortex configurations, which you can be tuned by simply changing the Fermi wave factor. Effect of the impurity breaks the Anderson theorem, and the results depend on the position of the impurity. And this here will give you a possibility to locally probe the superconducting condensate. Think that you use a scanning gate microscope where you can locally induce a potential, and then by simply changing this potential across your channel, you can simply see which condensates are important in this system. So thank you very much.
Since we are already over time, I suggest we take the discussion to the coffee break. Let us thank once more all the speakers in the longest session.